Let's talk about Raoult's law. Here's the mathematical expression for Raoult's law right here. It says that if we have a mixture of substances, then substance I, so whichever one that is, has a certain partial pressure that's going to exist above the solution. And that equals the mole fraction of I multiplied times what the vapor pressure of the substance would be if it was pure. Okay? Let me help you understand what that means here. So imagine we had substance A, and it's in a tank, again, and we've got the liquid phase down there, and then the vapor phase up there. Then we had a different substance B, and it also exists in its tank. And it had a vapor pressure above it too, and let's say it's a much denser or a much higher vapor pressure than substance A. Then PA star represents that vapor pressure for substance A if it was pure. And let's just say, for example, that it's 2 pascals. Okay? Then let's say that substance B also had a pure vapor pressure, and let's just say it was 10 pascals. Okay? When we make a mixture, let's say that it is 50% substance A and 50% substance B. So here's our mixture. It's got a 50-50 ratio of A to B in the liquid phase, but up in the vapor phase, we're going to have a different proportion of vapors. And what are those going to be? The partial pressure of A is going to be equal to the mole fraction of A in the liquid multiplied times what the pure vapor pressure would have been. So that's going to be 0.5 times 2 pascals, which is 1 pascal. That's going to be the partial pressure, the vapor pressure of substance A in the mixture. And then what would B have? B would just be the mole fraction of B in the liquid phase times what the vapor pressure of B would have been in the pure state, which is just 0.5 for the mole fraction multiplied times 10 pascals. Hopefully you see that it would have a partial pressure of 5 pascals. Now that's interesting because then that implies that the total vapor pressure of both of them is 1 pascal plus 5 pascals. So that's 6. So as you can see, it's exactly halfway in between what the vapor pressures were for the pure substances. A quick side note about real or non-ideal solutions. Those are solutions where Raoult's law is broken and does not apply. We will return to real solutions at the end of this chapter, but I just want to address it briefly so that you understand what would be the difference between a real and an ideal solution. Deviations from Raoult's law occur when the different components of the mixture interact with each other with different energies. So therefore, really different enthalpies, because if we're talking about interaction potential energies, then we're talking about differences in enthalpies. In particular, enthalpies of mixing, as you can see from these expressions down here. Let's think first about the ideal solution. Notice that there are equal numbers of blue and red particles up here in the vapor phase. That would imply that if we had pure red solution, then we'd have 6 of those particles up there in the vapor phase. And if we had pure blue solution, then we would have 6 particles of blue up there in the vapor phase. So ideal mixing would predict that if we had equal proportions down here in the liquid phase, then we'd have equal proportions up there in the vapor phase. And we would also have no more or no less than 6 particles total. But now when we have deviations from Raoult's law, then the mixing is actually going to change the potential energies of interactions between particles, because now A and B may have stronger interactions or weaker interactions with each other than they do with themselves. Let's consider the weak interactions first. If A and B interact weakly, that's going to promote more particles to exist up here in the vapor phase, and indeed that's what we see. And so a lower potential energy of interaction between the particles, if we mix them, is going to result in a higher vapor pressure total up above those liquid phases. If we, in contrast, have strong interactions between A and B particles, then that's going to promote more of them to enter the liquid phase down here compared to the vapor phase. And that's indeed what we see. When we have a favorable entropy of mixing, all of a sudden we're going to get a much lower total vapor pressure up above that liquid phase. Raoult's law is a limiting law, meaning it applies most accurately at the limits of very small dilutions. One last thing, it's worth noting that for an ideal solution, the enthalpy of mixing is equal to 0. And that will be interesting in a few slides when we look at the entropy and Gibbs free energy of mixing for a solution.